here, so.
The ring of charge. I need to first establish some of the rules we talked about before. We have to figure out a way of pointing to this piece of the ring and identify its location and how much charge is there. We're going to use that the amount of electric field from that one piece is equal to how much charge is in that piece times k divided by r squared. And that it's going to be in the r hat direction. That's the electric field thing. We're going to add up for every piece of charge. Oof. So, let's handle the easy stuff from the beginning, like charge density. Now, charge density tends to confuse folks. And I've had several students come in confused about charge density. Charge density is something you kind of make up to utilize in your problem. You don't have to do it this way. I know that this little piece of charge is a small amount of length of the overall hoop. You guys follow what I mean by that? That I'm taking a little piece of the hoop, a little arc length out of the hoop. And I know that the charge of the whole hoop to the entire circumference of the hoop has to be equal to how much charge is in my little piece divided by how long that piece is. You guys understand where all that came from? Now, I'm assuming uniform charge density. That the amount of charge on my little piece, my little section of this, is equal to the whole ratio, the entire ring's length, and the entire amount of charge spread around that ring. If you don't know where this comes from, if you can't imagine what I'm imagining, you can't let me move forward, because you will never understand the rest of this. So, do I need to go into this anymore about where that is or what that is? Because I'm saying that this little piece has dq amount of charge and is ds long. This is in meters. It's a length. It's a piece of the arc. A piece of the entire circle. And this is charge. It's in coulombs. Because this whole thing is also equal to the charge density. A character I just created so that I didn't have to write this every time. That's actually all it is. So the lambda, the sigma, the rho, that's so I don't have to write all of that garbage all the time. I can write one little symbol, and it's a lot easier to write that symbol. Now, I got musicians in the room. Who's ever seen a guitar before? So Carlos hasn't? I'm sorry you haven't. We should help you see one. So if you've seen a guitar, you understand that the strings are not all the same thickness. Right? Now, if I take just the E string and I cut off a centimeter of it at the top of the string or at the bottom of the string, will either one of those centimeter pieces weigh a different amount? They're all from the same string. Will every centimeter of it be the same mass? But will they be the same mass as the G string? No, because one of them is thicker than the other. Follow that? Is that okay? That's charge density. Just instead talking about mass density. The thicker strings have more mass density than the thinner strings. It's the amount of mass per unit length. That's how you buy guitar strings. They don't say it like that. They put a little letter on there because we're too dumb to figure it out, apparently. Every good boy does fine. But at the same time, they could sell them to us in terms of mass density, kilograms per unit meter. They just don't. So it's the same thing here. We're creating what the density of the charge is on the ring. I need that because I want to know how much charge is right there. So right now, I'm going to do it the long way. dq equals q over 2 pi r ds, or lambda ds. Which one do I want to write down all the times I'm going to have to write it down? You understand, it's going to be lambda ds, right? Because I've got to write this like 10 more times. So that's why I want to use this one. It's easier. And I'm all about making it easier. Now, this is R. I'm at the point to this piece. There's a couple of ways I can point to this piece. I could travel along R. The problem is that R is the same for every piece of ring. That's kind of nice. You guys all see that too, right? But I bet they want me to have this in terms of something like this, Z. That's probably what they would really like. But it seems to me that R is going to be equal to the square root of Z squared plus R squared. Pythagorean theorem? I know they're going to want this in terms of Z. I remember the problem. It was totally in terms of Z, isn't it? We'll switch it over from Z to X. Doesn't matter. I need a way of writing R, because R is the actual distance between the point P and where the charge is. Now, as I'm beginning to build this, I realize I have a way of writing the amount of charge. It's in terms of S. I could, because this is circular, break this into like R and theta if I want. But I want to point out something. Does it make a difference in how large the electric field is whether I choose this piece of charge or this piece of charge? They're all the same amount of charge, and they're all the same distance away from point P. You guys see that, right? So every one of them is going to be the same contribution to the electric field. So whether I write this in terms of ds, because they're all the same size ds, or I write this in terms of the radius and d theta, they're all still going to contribute the exact same amount of charge. It's not like the other stuff we've done where different points on the circle might apply a different amount of charge. All of these points are applying the same amount. So I can just add them all up, except for one glaring problem. The electric field isn't along X. The electric field is this way from that charge. That's a problem for us, isn't it? But is there symmetry? Yeah. Is there another one that happens to be right here that's going to produce an electric field that is symmetrically off axis? Yeah, so I don't really need to worry too much about it. All I do need to do is recognize I need this amount of dE, this portion of it. Probably a trig function will do that for me. Yes, sir?
How would it be different if you were calculating the electric potential of the, because I think that's what the first part of the
Well, the biggest difference is that if it's the electric potential, it doesn't have direction. So I don't have to scale it by the cosine like I do for the electric field.
So like you would just
I'd be done. Yeah, just add them all up. All right, so obviously left off. But the way I see it, we have an expression here that indicates our framework for finding a part of the total electric field. We have an expression here which will yield how much charge a small piece of the hoop will have. We have an expression here that tells me R is going to be a constant no matter where we are around this ring. And this piece right here seems to help us deal with the direction portion of the electric field, recognizing I only need to deal with the components of the electric field that are along X, otherwise known as cosine of theta, where this is theta. But it does seem like I'm introducing another variable into our work here, aren't I? Theta seems like the introduction of a variable. And I don't want to introduce more variables, but I think we could probably express cosine theta in terms of variables that are already there. Do you think we can? I'm very sure we can. And this is one of those pieces where you'll notice we do this every single time, anytime we can. We try to express the angle as something else. Now, we will face ones where we do the reverse, where we express some other things in terms of the angle, but I think we can see that this is the adjacent and this is the hypotenuse of a similar triangle to the angle expressed on the other side. Do you guys see that? And since I only need adjacent and hypotenuse to express theta, I think I have all the pieces in place to assemble the integral. So I think that's what we're going to do next, is we will assemble this integral. Now, what would be really nice is if I could just duplicate this and use it again for the question I know that's going to come up. So there's got to be a way, some kind of, procedure here. There it is. Good. So I don't want a new one. I want to duplicate the one that's already here. So is that a thing? Maybe, maybe not. Let's putting this together, and I'm going to do so by shrinking all that super small, because I don't need to see it anymore, and assembling the integral, dE equals. All right, for dq, am I okay to write lambda ds, or do I have to put q over 2 pi r? Be honest. I don't want to confuse anybody. Yes, so I'm good. All right, good. Thank you for replying to the question. It's nice when you say a question and an answer appears, even if it's only in sign language form. I'm not supposed to look at one of those. I've been trained not to look there at the circle. So I carefully am looking off to the side to ensure I did not look at the circle. Do you know what I'm talking about? Yes, see, I got many of you.
Did anybody actually hit you?
Really? Felony striking a teacher? Probably not.
Exactly. That's why I was heavily confused.
But it's not implausible. But no, I really have not yet been struck by a student in a long time.
What's the story?
It's not that interesting. I'd love to say I have some way interesting story. I do not.
I've been.
I mean, I have other interesting stories. That's not it. I'm just trying to put all the pieces together.
Yes. No.
And I think that's it. Is that all the pieces? I believe we're good. I've got the part dealing with the cosine. I've got the part for r, and I got the part for dq. So yeah, all the pieces. Now, here's where I'm going to do something different than the last time. Remember, the idea now is we have to add all of these things up for each piece of the ring over the course of the whole ring. Yes, sir?
Do you need K?
I do need K. Thank you. See, I knew I was missing something. So, if you look across all of this, there is nothing in all of this whole huge thing that has anything to do with which piece of ring we're talking about. Do you guys see what I mean? Every piece of ring is contributing the exact same amount of electric field and the same amount in the direction of x. So whether I'm choosing this piece of ring or this piece of ring, every piece of ring contributes the same amount. The reason that's important is when I decide I want to add up over the whole ring, the left side is just electric field. But the right side, I can take anything that is constant, that's not changing with regards to the piece of ring I'm looking at, and pull it outside the integral. So that means lambda comes out, and k comes out, and the x comes out. None of those have anything to do with which piece of ring I'm looking at. On the denominator, the x squared plus r squared to the 3/2 power comes out. I just combine those things. We okay with that? So that means I'm left with adding up the entire length of the ring. So I guess I'll start at 0 and go 2 pi r around the ring. Since every single piece of length adds the same amount, I just need to add up the whole length of the ring. You guys follow that okay? It's not an unreasonable argument. And this is a method of doing this. When you're writing stuff in your notes right now and you want these notes to have any value at all, you should describe why we can just do this. It's because we're adding up over an entire length. That's what DS says, add up the entire length. Each piece of length is contributing the same, and the total length is one circumference. If it's a ring, adding up over the length. Now, if each piece added a different amount of charge or something like that, we wouldn't be able to do that. But each piece is adding the exact same contribution, so I can just add up the whole length of the ring. That's really it. Now, that means at the end of this, I'll have lambda times k times x all over all this garbage, x squared plus r squared to the 3 halves times 2 pi r. But I can't actually have this as my answer, because lambda was not a variable I was allowed to use here. Lambda was a construct that I created to hold the charge. In fact, we know that lambda is q over 2 pi r. So although the truth is we're multiplying by 2 pi, we're also going to be dividing by 2 pi r in a minute when we substitute back in for lambda. So if I substitute back in for lambda now, I just moved it over there, then the 2 pi r's cancel, which I'm not really surprised it leaves me with a value that represents the entire amount of charge. So I know you have to rewrite it every time, but I don't. There we go. That's got to be the answer. And I kind of like pieces of the answer. There's things about this I think are interesting. Like, I think being in the center of the ring, there should be no electric field. And I'm going to point out that when I set x equal to 0, there's no electric field. You guys see that okay? I'm also going to point out the other extreme, that when x is much bigger than r, the denominator is dominated by x, which means the denominator becomes x cubed. And since I have an x on the top and an x cubed on the bottom, if x is much bigger than the ring, then the ring becomes a point charge when you're far away. I would kind of expect that too. Yes, sir?
When I tried doing this, like on the homework, I didn't sub dq for lambda ds, I just left it as dq. And then when I took the summation of that, I just got q. Am I allowed to do that?
You can do that only if, when you do that summation, you know that every piece of the object you're summing over, A has the same value of charge, and B is contributing the same way to the total amount of electric field. In this case, it does that. But if it had been a different shape, where maybe each piece is a different distance away, you wouldn't be able to do that. You'd have to sum over the geometry of the object, so that as you sum each piece, its contribution based on its location would be added in its relevant way. But this one, every piece is the same distance away, so sure, that would work out. In the same way that if we had an arc of charge, and we were looking at the electric field at the center of the arc, each piece would be the same distance away, so you could sum up over dq, and that would be fine as well. I do it the long way. because there's every reason to believe they could ask us a question that would involve us having to deal with the fact that the charge could be different for every piece. Like, if I set it up like we've done here, we could, same procedure we just used to figure out not one that's along the center, but maybe one that's maybe off to the side here, a distance x from the center, but located along a diameter or a radius. Now I couldn't use dq for every piece, because this piece here, its location for this dq is different than this piece over here. You follow what I'm saying?
Yeah.
Now, they've never asked this question before, so I wouldn't expect it. But I will say that this question is very symmetrical. Do you see it, all the symmetry there? For every piece I have here, I have another piece just like it over here. But this would produce a very, this would be a challenging question to do, I think, for you guys. I think for me too. So if you're interested in a bit of a challenge, try it. Some of you are catching on to this, see what you get. I'll try it too. But if you're barely grasping, then don't worry about it. I've never seen him ask this question. It's an interesting question, interesting thought. We have to redo the.
Finish like explaining all of it. It was just an additional question.
No, that's now, because I'm gonna change parameters a bit.
Okay, I was gonna ask if the ring had thickness.
This one, no.
No, not like this particular drawing, but like what they like. Out of curiosity, like if the ring in the previous like how we did in homework, if it had thickness, like thickness W, right? Or if it was like a tube that was.
Yeah.
No, I'll wait till you the form of a ring.
Tube. Wow, that would be tough. They've
Yeah.
asked.
Can you do it?
I don't know. I haven't tried. It's hard to describe that geometry. If you're talking about like a donut,
Yeah.
so that's what she's really describing, or what the official word would be a toroid, a charged toroid. Then, how do you define how far each piece of the volume is away from your given location? That's actually a pretty hard thing to define. So I probably wouldn't do it that way. I would probably try to find a way to break it up into different pieces. Like maybe find a disc off center at that point. So I want to finish the question. The question was, I'm not sure the question was about electric field. Michael said the question was about electric potential. So this is how you do the electric field one. But to do the electric potential, you gotta do something different. But the electric potential is not necessarily harder, it's just different. Because instead of having this function as the electric field, we're starting from a position of the electric potential for a point charge. And it's not a vector. So remember, we've proved the electric potential for a point charge is just QK over R. And it's not a vector quantity, so you see no R hat there. We can do everything else exactly the same. We can still break each piece up into an individual point charge. We can take each of those pieces and then attempt to find their contribution. But one important distinction is that each piece contributes to a small amount of electric potential at this point. It's not a vector. So there's no cosine involved at all. So every piece is the same distance r away. They're still x squared plus r squared away. But I don't have to scale each amount of electric field to be part that's down the center, because there's another off-axis electric field that's canceling it out. The electric potential is a scalar quantity. It just adds together. So in changing from the electric field to the electric potential, a lot of times our integrals are easier because we don't have to deal with the electric field direction. We just sum the whole part up. Now, at the same time, I'm expecting a drastically different answer. the electric potential should not be 0 at the center. Even though the electric field is 0 at the center, I think it's going to take energy to get to the center of this ring. Do you guys understand what I'm saying here? I think that you should question your ideas here. Don't you realize that the electric potential at the center of the ring is going to be a difficult place to attain because you're working against the electric field the whole time, except for the very end. So I'm sure the particle has energy on the way there. And it's going to take energy to get there. So let's go ahead and do the math on it, because we're almost there now. We have to assemble the electric potential, which is going to be all the same principal pieces, except no cosine, and a slightly easier denominator. So, oops, what am I doing? I'm going to put lambda. Lambda ds k all over x squared plus r squared to the 1/2 power. Oh, that's it. Now, lambda k x squared plus r squared to the 1/2 power, all of that stuff is constant. It's the same for every contribution to the every piece of the ring. What?
The question asks as a function of x, so even if it asks as a function of x, would x still not? For the calculations, would you treat x as not changing even though it asks for it as a function of x? Because that's where I got confused.
Am I going to answer? Okay, can I get in there? Does choosing an x change where you are on the ring?
No.
Exactly. X is being substituted in for r, but x and r are the same distance for every point on the ring. So it is not a function of the integral. It might be a function at the end, but it's not a function of the integral. Meaning, when I add each one of these points around, am I going to be left with an expression that has x in it?
Yes.
Then that's a function of x. It's also a function of r. It's also a function of q. Every one of those things are in the final answer. I can see how changing any of those affects the answer. That's what an expression is. So, in this case, at the end, if there was no x in my function, I'd have to decide whether I actually did what they asked or not. So that's why I wouldn't leave it in terms of r, because I wouldn't have an expression that was in terms of x at the end. I'm still going to find the integral of both sides. I'm going to say this produces the entire electric potential on the left. Notice I'm not putting a delta there. We are using the expression for the electric potential of a point charge, which we proved from a place far enough away where the electric potential was 0 at the start. So this is not a delta. This is not a change in potential. If I wanted the change in potential, I would have to have a starting location and an ending location. But I'm not doing that. I'm assuming the total electric potential from a place really far away. Everything there, just about, except for ds, comes out of the integral. And again, every single piece is going to add the same amount to the total electric potential of the system. So I'm just going to put 2 pi r there. And I think I probably shouldn't. I'm not going to cut to the end. I'm going to go ahead and say this is times 2 pi r. Add up around the entire ring. But then I'm going to remind you that lambda and 2 pi r are going to work together to produce just q in our answer. Just like before, we had the same start. So that's going to make this become q. So is this a function of x? I think so. It's a function of x. Did I have to integrate x from one location to another? No. So I'm not integrating due to x, but I do create an expression due to x. When x goes to 0, the electric potential is not 0. Do you guys see that? Interesting though, when x goes to 0, you are left with a value that looks like a point charge that you are a distance 1 radius from. Do you guys see that too? And I don't think that should be thrown out. Remember, the electric potential for a point charge is QK over R. That's electric potential for a point charge. Well, when we are at the center of the ring, all of the pieces of charge are the same distance away, R. So the electric potential there works out like that. What's interesting about this particular situation is that it's an unstable, like an unstable location in space. As long as I put a positive charge right at the very center, that positive charge will stay there because the electric field on it's 0, so there's no force on the particle. But if you just give it a little push, then suddenly there's going to be a huge force on the particle. Do you see that? I mean, just look at the picture a little bit there, but I've got all this stuff in the way. Oh, that's not what I wanted. So let's just clean this up for a minute, get all of this out of the way so I can just kind of focus. All of you gone, bye-bye, all of you. All of you down there too. No distractions. Just happy little clouds. There. So if I take a small charge and put it right here at the center, it has an electric field of 0 at the center. So that piece of charge will just stay there. But the moment I push it a little bit outside, it's going to experience a net force in this direction that will accelerate it away from the charge, or away from the charged ring. So let's say I do put a small charge Q there around a ring of charge Q. I'm extending the question a little bit. This could be used as like a particle shooter. All I have to do is give the particle a little tiny push out of the center, and it's going to shoot the particle away. You know, you can figure out how fast it will shoot the particle. I know you don't see that, but I want you to. The reason is because we know the electric potential at the center, which is QK over R squared at the center of the ring. Oh, just R. At the center of the ring. Potential energy is equal to Q times V. This is the amount of potential energy this particle has once I get it to the very center of the ring. This is the definition of electric potential. It is energy per unit charge. When I give it a little push, that force is going to do work on the particle, converting this potential energy into kinetic energy. Which means that after some time, the total amount of energy that I have in the charge will be converted to kinetic energy in the charge. Seems to me I could probably figure out how fast it was going if I know, say, the mass of the charge. See, once you know the electric potential, you know how much energy charges will have when they're placed at that location in space. It's the same for like potential energy. If I know how high something is going to be, then I know by MGH how much energy it's going to have. It's the same here. One of the differences is, though, this works for a positive charge. It's an unstable point of equilibrium for a positive charge. It's a stable equilibrium for a negative charge. The negative charge has the same amount of energy there, but the energy works out to be negative. That has to mean something. And it does. It tells us points of stability. If I have a negative charge here and I give it a small push, will the force be this direction? No. If I give it a small push, the force will be in the opposite direction. Which means if I give it a small push, this is going to turn it into an oscillator. And it will oscillate back and forth between there. If I was a smarter person, we could probably figure out the period of oscillation. But maybe after we've covered that in, more detail elsewhere, we can come back to this problem. Because it would oscillate back and forth. Some models of atoms have been based on this kind of idea, this kind of concept. The ring of charge, it's tough. Yes, sir?
Since it has electric potential like in the center of the ring for a positive charge, doesn't that mean it has velocity? So which way is the velocity going?
For the negative particle, or for the positive one we just did?
Yeah. Like, but which way is the velocity if it's at the center?
If I put a negative charge at the center,
A positive charge.
if I put a positive charge, okay. If I put a positive charge at the center, while it's in the center, it'll have no velocity. Because it's in equilibrium. The net force on it's 0. But it has this much energy. This much energy. Right? So if I want to convert that energy into kinetic energy, I would have to give it a small push and displace it a small amount away from the center. Any small displacement from the center will result in there being a force on the particle along the line x. And that's what will convert this energy into kinetic energy. But I need to give it the first initial displacement to get it out of the center. Does that make sense?
Yeah, I get it.
So it doesn't have a velocity yet, but what we're kind of saying is that if we can displace it, the maximum velocity it will attain will be when all of that potential energy is converted into kinetic energy. So sometime far away, it'll have that velocity. And in terms of small particles like this, that's not very far. It doesn't have to be a universe away, just far enough to be out of the influence of the other charged particle. For it?
Yes.
Yeah.
So there's a lot of distraction when it comes to sketching a graph. And don't be too distracted by it. So it's probably, what was it, potential versus position? Is that the graph they kind of wanted? I don't have the problem in front of me.
I think so. Let me-
Here, I can see in a second.
Oh, it's going to take too long. So when we
it
have...
was E. It was,
On the y-axis.
yeah, on the y-axis, it was E of x.
Okay, so they wanted electric field, not electric potential. Electric field is actually more interesting than electric potential then. So we get the Q is on top, K is on the top, and we're going to get this x squared plus r squared to the 3/2 and another x on the top like that. You're really graphing this. That's what you're graphing. And it's, you should try it. You should put it in your calculator. Just use, 1 or something for r. But I hope it's not a surprise what you're going to see here. We already know it's going to decay as an inverse square when x is much bigger than r, and it's going to go to 0. So we know it has to start at the origin with an electric field of 0, and it has to end with something like this as you get far away. Now, if you don't want to put it in your calculator, just listen to those things, right? That it has to start with an electric field of 0 at the center, and it has to decay back to 0. What possibilities are there? We know it's going to be a smooth curve, so the only possibility is to try and connect it to some kind of smooth curve. Mathematically, it's got to look like that. And it has to be on the positive side, and it has to be on the negative side to be symmetrical. Because the electric field has to push it to the left if it gets displaced to the left, and push it to the right if it gets displaced to the right. Is that what your calculator showed you?
Yes.
Yeah.
You have to zoom in just right to see it though. Alright. Like, if the disk were here, and the line through the center is here. So if this was one cross-sectional piece, that disk, I'd probably try and find its contribution to the electric field as a whole by taking a small area here and finding each little piece's contribution to electric field across that disk, and then rotate it around the beam. That's what I would probably do. But even that, finding out, doing that problem, just this disk, is actually not as easy as it sounds. It's actually pretty tough. There's not nearly any symmetry here. If it doesn't seem like it, but there's very little symmetry here. And that's what makes it hard. Because although it looks like it's symmetrical, it's not. It's symmetrical about a line drawn this way. But we know we have another disk, down here someplace. So I only want the contributions to the electric field that are this way. That's asymmetrical compared to this disk. So it sounds like it might be easy, but I don't think it is. So I'm not really sure how I would set it up. I'd probably have to find this electric field from this disk, and then take every disk and only deal with the cosine of that after I've done it for one disk. I think that's hard. I'm not sure I can do it. And I'm not sure why. You have to understand something, the relevance of these things. Is it really going to be different enough from a one-dimensional ring, ring with no thickness, to matter? Probably not. Is there anything in space that's a charged toroid that's thick enough where it matters? It's still going to have zero electric field at its center. It's still going to reduce down to a point charge far away. There's some intermediate stuff in the middle that might make it a little different, but a problem like that, if I'm going to waste waste is wrong. Mathematical stuff like that's not a waste, but if I'm going to use my time to figure that one out, there are other problems that are more interesting that would be worth your time. And I just don't see this as one of them. But, oops, I didn't mean to make that many. They've asked this question before. Actually, no, they've not asked this particular question, but they've asked one similar.
Yeah, kind of like that. But not with two. Two would be difficult.
So yeah, two would just be different. Two would just be a bunch of rings
Yes.
that are getting further and further away. It actually wouldn't be as hard as it looks. This would be harder. But this would also just be a bunch of rings, concentric rings. And so we could just do this one by doing a ring once and then adding up a bunch of rings.
Oh no, I was talking on a tube. I mean, like you had a tube and you made it into a ring.
Oh, okay.
Connecting it on the other side.
No, we would never have that question.
Okay.
No. So that'd be hard.